Afternoon, everyone. So, after a long discussion on ML and DL techniques, where we talked about different types of algorithms and computation methods, now we invite Dr. Santhosh Kumar Vishwakarma, who will talk about in memory computation for edge AI applications, opportunity and challenges. Professor Vishwakarma did his BSc degree in electronics from University of Gorakhpur and MSc in electronics from Devi Ahilya Vishwavidyalaya Indore in 2001, followed by an MTech degree in microelectronics from Punjab University and a PhD degree in microelectronics and VLSI from Department of Electronics and Communication Engineering, Roorkee in 2010. Then he was a postdoctoral fellow at University Graduate Center, Norway. From 2010, Professor Vishwakarma is with Department of Electrical Engineering, IIT Indore, where he is a professor now. He is leading nanoscale devices and VLSI circuit and system design laboratory there. He is engaged with teaching and research in the area of energy efficient and reliable SRAM memory design, enhancing performance and configurable architecture for DNN accelerators, SRAM based in memory computation architecture for edge AI, reliable secure design for IoT applications, and many more. So I welcome Professor Vishwakarma and over to you.
Yes, thank you, Professor. So, first of all, thanks to IIT Tirupati to invite me in this holy city. I came yesterday and then onwards, I am taking roaming of the city and that to the temple. And it's a challenge for me to you guys to make live, and that is the tea time is close to 3 o'clock or so, right? So you are from which background? I mean, computer science or electronics, electrical? Mix. Okay. Okay. Yeah, so it will be more challenge for me to explain this hardware concept, but I believe that you will enjoy. I mean, at least because as of now, I was just listening to Professor Rama that people are talking about more about software side, but in system design, we need hardware, right? So what are the things we have to take care of if you are really thinking of to design and develop and something workable model? Without hardware, things are not working, right? So little bit knowledge about hardware will always make your interest live. So probably I will try to bring the hardware aspect of these machine learning or AI aspect. What are the hardware availables, and even if hardwares are available, that why we are doing edge computing and so on and so forth, right? So many things you may have covered, but I will try to touch up not in detail in technical insight, but what are, since this is a new area, so I thought I should talk about opportunities and challenges, right? Little bit about contribution what we have made, not that much. So this is a group where I belongs to in IIT Indore. So where we primarily work on memory design, right, especially on the static SRAM memory, and there also we try to make the edge AI computing using SRAM only. The last 5 years we are focused on the accelerators, right, and then in the past couple of years we have made lots of project and we have designed couple of chips for IoT applications, and there also we talked oftenly about reliability aspect of the chip design, because if you are designing any circuit or system, so that should be reliable. So we are also touching 2-3 PhD scholars on reliability aspect of circuits. So this is the group where I belongs to. Coming to the research activities from 2010 onward, so what we have started, that we have started with the devices. Those who are from electronics background, they may understand very easily that what are these MOSFETs. So since this is, so if you just see this diagram, this is FinFET structure, but it comes from FinFET. So FET stands for field effect transistors. So but early days, right, many years before, when the chip things started, the concept called MOSFET, right, metal oxide semiconductor field effect transistor. So this was the fundamental block in semiconductor devices and later in circuit and systems, by which you can realize any complex circuit. Okay. So, but over the period of years, right, when you try to have more functions into the chip, more operation into the chip, right, so we need a huge number of devices on a tiny chip. So, for example, if you are considering a chip size of 5 millimeter cross 5 millimeter, okay. So, in this tiny chip area, right, we have to have lakhs and lakhs component. So, how to do? So, initial days, for example, if this is the MOSFET, okay, and this is the channel, and this is the silicon dioxide, and this is the N plus, this is the N plus, alright, and then of course silicon dioxide, and this is the gate, this is the source and drain, whatever you can change, the source and drain can be interchangeable, right, and of course this is the body, and this is the channel through which the electrons can take the movements. If you are talking about N-type enhancement type MOSFET, okay. So there are various categories of the MOSFET. The first category was the enhancement type, where we try to enhance the channel or create the channel by applying the proper potential on its gate. So I am just brushing up the semiconductor devices and physics, okay, just to generate the interest. So the electrons used to go from source to drain, and hence the current used to flow from drain to source, right. This is the fundamental physics behind this. So since we are trying to create the channel, right, so that the there should be a path, okay, just between silicon and silicon dioxide, okay, and that the number of electrons which are flowing from source to drain depends upon the applied electric field, and hence this name is called the field effect transistor, because the current conduction mechanism used to be controlled by the applied vertical electric field or horizontal electric field, okay. So you try to shrink the device dimension, maybe the channel length, this is called the channel length, this one, the width and the depth, and many things are there, so that you can accommodate large number of MOS devices in a tiny chips, okay. So as a result, people evolved various MOS transistors, where the FinFET is the one which is commercially available in many processors which we used to have in our mobile phones. Qualcomm Snapdragon 22 nanometer technology node, you must have heard of it. So over the period of years, people have thought of that if you shrink these device dimensions, right, so what are the alternate options called the advanced MOS devices, okay, advanced MOS devices, right, where if you scale down the device dimensions, right, and if you are supposed to operate at lower voltages. Early days when the channel length was for example 180 nanometer, okay, then applied voltage was 1.8 volt, okay. Now since we shrink the device dimensions, so you cannot operate the same device with shorter length at 1.8. So you have to scale down even this from 1.8 to, for example, 0.2 volt or 0.5 volt, right. So everything we are syncing, right. So electric field is supposed to be maintained within the device, okay, but forget about all those things, but you try to understand that people in the research community try to evolve various non-conventional devices. Conventional device is this one, the MOSFET, which was started 40 years before, 60 years before, right. In fact, the concept of the MOSFET was in 1930, right, but at that time the fabrication technology was not available by the research community or even fab labs. So then the JFET evolved, junction field effect transistor. Couple of years JFET comes, then over period of years 1948 or so BJT evolves, right, and then in 1960 or so the MOSFET, even though it was invented in 1930 or so, close to that area, right, that era, but in 1958 or something the first monolithic IC fabricated. So it took years to evolve the chips, and now over the period of years, if you scale dimensions, try to see more functionality and so on and so forth, people investigated various non-conventional devices where FinFET is the one, tunnel FET is the one, and gallium nitride and so on and so forth devices evolves. Okay. Now we have talked about foldable devices also. So foldable devices, now silicon is not there. So as of now people are talking about all materials silicon. Now we may have seen all Samsung foldable lavender phones, right? Smile, is 3 o'clock time means let us charge. Lavender phones, so it's costing around 80,000 rupees, more than that, right? So how foldable comes? Lots of OLED are there, OLEDs are there, light emitting diodes, right? So with the semiconductor materials era also devices developed and hence the product developed. Earlier we used to have a flat screen, now foldable screens are there, or you can say curved LEDs are there, right? So many things evolve and hence people started research from devices to materials and try to investigate some circuits and later bigger circuits and try to make some kind of these boards having various part and then of course chip. So this is the one board which we used in our lab called the zinc board, which is this board is called the system on chip board. So what I am trying to explain is that that last 12-13 years we started working on the devices, device circuit co-design, couple of chips we have fabricated. Then for IoT hardware based experiments we have used couple of boards and so on and so forth, where we have interfaced couple of sensors, and then we have realized couple of system on chip. For example, this is the IC, right, which was tested for one of the biomedical application chip called IoT wireless sensor node, right. So where, for example, this is the ADC block sitting, this is the memory block, and there are many other blocks are sitting on this 5mm cross 5mm chip area. Okay, but what we have done and what we have learned last couple of years that as of now we were trying to interface only signals of only not really image or even video or audio. But with the evolution of these computer vision, just now Professor Rama was talking about, where we oftenly interact with the images as a data sets, right. So when you are interacting with such a huge data sets with your hardware, right, so it is not so simple even for the chip designer that the normal chips will be sufficient enough to process such a huge data or to store that large number of data, okay, in the same chip. So people thought of, can we have a sophisticated chips or a very appropriate chip which has a capability to deal with the images or the audio or video, right. So how to design those kind of chips, even a small thing, for example power distribution or power dissipation of the chip, there also we have to evolve the machine learning techniques, right. So the entire history of the VLSI chip design is changed now last 2-3 years. Okay, so now people are thinking what should be the hardware, how to design various hardwares or various sub blocks of a complete block. For example, a processor. So in processor there are multiple blocks, right. So for example, addition is the one operation, adding 2 bits, right. So how to do addition or multiplication of those 2 bits or even multi bits, right, multiplication, how to do. So all those mathematical processes or the operations is also performed in a very systematic manner, and ultimately as a researcher or as a product engineer we have to store all those huge data in some hardware. So what are the different techniques by which you can store or retrieve the data rather than the von Neumann computer architecture. So in von Neumann computer architecture, so there is a processor, okay, and there is a memory sitting on the chip, right. So processor used to process the data, right, and this is the memory element where the information are supposed to be stored or retrieve the information, right. So both the things are little bit away, right, but since there are various applications where these techniques may not be applicable, so how to do? So rather than von Neumann architecture, right, if the data used to go from here to here, it will take some time, called the latency. So to minimize this latency, people are trying to come up, can we have both the things on the same chip? So in memory computing, so computing used to be happen in the processor and storing here. So can we have the everything in memory itself, where no need to travel the data? So that is what the topic of the relevance of today is, right. But at the same time, since we are dealing this complex inputs can be image or something, so what should be the complete hardware? And as a researcher, sometimes it is very difficult that we always look forward for the GPUs, right, or sometime even bigger than that, right, to train the data. That required the money as well, right. So how with the small FPGA boards, right, you can train the bigger data, that is also a topic of the interest. So we have developed couple of algorithms where neural networks, bigger neural networks can be trained, and you with a small money budget, from not more than 20,000 rupees board, right, you can easily train the model, and accordingly you can improve the performance of the network, right, on a particular data set. So we will discuss all those things, but what I am trying to explain is that our journey was with the devices, materials till system. Okay, coming to the exact topics, right, people are talking about AI, and why? But because we need to have some motivation things, right. So motivation is like that there was era of internet, okay, where deep neural networks was not really that much, but it is forecast that in the coming years, right, the DNN market is going to be really changed like anything. So DNN market start from 2020, before that I should say. So in next under 20 years or so, we will have a huge jump in this area, in deep neural network, okay, called the deep learning, okay. And this also you can understand in the worldwide picture, if you see, right, in next couple of years. And so this is the North America, right, and then Western Europe, and then of course Eastern Europe, Asia Pacific market is this. So in Asia Pacific market, this AI accelerators, or you can say the AI chips, are going to a big leap. So that also sometimes motivates us to do the research, okay, in AI accelerators, because if money is there, then definitely research will be there, product will be there, right. So this is how the trend of the artificial intelligence and the AI chips, okay. So this is just to motivate you guys. And there was one word called the edge. So what is happening in the edge? In early days, even now also, for example, the servers are there, or you can say the cloud is here, right. So cloud is what exactly cloud? A huge number of servers sitting remotely, right. So for example, if you do some computation, right, and your all the information used to go and compute on the cloud, and according to your request or the user needs, so data comes from the cloud to your machine. So it used to go from your end user to the cloud, and it comes. So that takes the some time called the latency. But there are various applications where even this millisecond time may make a difference. So for example, autonomous car, okay, the sensors are placed in the car, okay, and the car, if the car is passing through various ways, okay, so it used to encounter various images. Accordingly, the car should work, right. So for example, the turning image are there, or ahead image, or lidar sensors are there, whatever sensor you are using, right. So what I am trying to say, you have to take the decision right away, quick decision, right. So for that, a particular hardware is needed, right, no processor computing, it should be on the same chip and everything. So and Google Glass is the one example, right. So if you are wearing this Google Glass, okay, so a small chip is there, and chip used to interact with all the images which are encountering, and accordingly it used to act, right. So that is what, like, of course, mobile, wearable, IoT devices, almost all the connected devices are going to have the AI chips, and that to the edge. For example, this light is there, or bulb is there, right. So bulb, you have IoT devices, and there also, and few years before, the sensing elements sense the data, and it used to send to the cloud, and then based on your requirement, it used to come the decision to the user, but it takes some time. But nowadays, for example, safer city concept, right. So in safer cities, cameras installed in the city, right, and images are going to be captured by what the movements, something or whatever, right, and then you can take the decision very quickly. For example, the police officers or the crime police or something has to take immediately action, right. Otherwise, there are various applications, strategic application, for example, where the sensing element, computing element, and everything are sitting on the edge. So for all those edge devices, what should be the required hardware? I mean the chip. What should be the philosophy that we are talking about? But just to motivate you that these things are is very, very important, okay, on edge intelligence. And I just now talk about the issues. So where do we have inefficiency comes from? So I said, of course, the algorithm, circuit and systems which are sitting in the chip over here, and the hardware architecture. So if you can think of these circuit and system part and the algorithm side part, right, which by which you are designing the hardware, right, then probably you will meet the requirement of the edge computing. Okay. I was just talking about the edge. So in the cloud, what we does, right? So for example here, right? So this is the cloud computing, but this is the edge one, right? So no need to go on the cloud, things are over here, and accordingly immediately you have to take the decision, right? So latency time is very, very less in edge. It's not a much difference, only maybe milliseconds or fraction of second, but there are various applications where you can think of, okay. So, but of course, what are the benefits of the edge computing? Though, of course, enhance the data security, okay. Low pressure on the bandwidth, even internet speed or the bandwidth is very low, you can operate, because sending the data from your sensing elements to the cloud, it needs huge data or the bandwidth. But there are various applications, for example, border security areas, right, where sensing element would be there, even with low bandwidth, you can sense the information and train the information, right. So of course, reduce latency is the one, low cost data transmission, increased availability. So these are the couple of benefits, and accordingly you can design the hardware, okay. And this is the one example of the edge AI, right, and these are the latency what we are seeing in the market, okay. Now, so these things we have just spoken about the relevance of the subject and what kind of hardware do we need, right, on the edge computing. But almost all the places, many speakers may have spoken about the neural networks. So I will not spend much time, but just to brush up that the DNN, lots of inputs are there, and these are the hidden layers, okay, and these are the outputs, okay. This is the fully connected neural networks, okay. And for example, if this is the one neuron, right, model, right, of, for example, MNSC data sets. So this is the 10,000 samples of 0 to 1, it is easily available, right. So for example 9 can be written in multiple ways, right. So how 9 can be recognized in its output, that is what is being shown over here, right. So for example, this is the input and they are the hidden layers, there are neurons, large number of neurons are there, and then ultimately you can get 9 or whatever it is there. So but in this process you have to pass on this complex theory into some hardware. So what should be your hardware? That is the main interest of your story, okay. But if you start designing a simple neuron, one neuron, okay, where images are supposed to interact, so we need to have the first block called the MAC unit. MAC means multiplication and accumulation unit. So what is that? So for example, this is the one input x1, and this is the weight of the neurons, because here you may have learned and maybe understand the fully connected network or any kind of CNN or RNN, whatever it is there, every neuron have its weight and bias, okay. So that comes from the training, okay. So if neurons will have some input, any number for example, and some weights, so they need to be multiplied. For example, x1 into W1, so that is multiplication happen over here, plus x2 into W2 and so on and so forth. All the weights are going to be multiplied by the input, and accordingly you can get. So what is this? This is a multiplication. This is a multiplication. So that is called the multiplication and accumulate, addition. So addition is also coming over here, addition, right. So it seems we understood very nicely as of now that to realize a one neuron in the hardware, right, we have to have a little bit knowledge about the multiplication what we have learned into the digital electronics. So it's in digital electronics we may have learned how to multiply 2 bits or even multiple bits or multi-bits, right. And then addition, of course we know, okay. And then to fire each neuron we have to have some activation function. So activation function can be of different varieties, sigmoid, tan hyperbolic, Swiss, ReLU, many things are there, right, available in the market. So depending upon your application, we have to have some activation function and MAC unit, and you can start thinking of designing one neuron, then multi neurons, and then how to use this activation function, in which way, how to use these hidden layers, right? So we have to introduce some concept. For example, we have used this is all about, once again, MAC unit implementation, activation function, like for example high performance neuron architecture. So a couple of my PhD scholars, they have worked upon how to enhance the performance of neurons. Okay, so we have used various philosophy. For example, reused feature. So the same activation function can be used for multiple neurons, so that we can reduce the complexity of the network, and with lower hardware we can deal huge data sets. So those exercise we have done, like here we can see the sigmoid function, 10 hyperbolic function, and then in the neuron architecture we have improved, right? And this is how the codec algorithms, and then we have put couple of multiplexer, and then you can find, for example, this is the 10 hyperbolic block, okay, and this is the sigmoid block, okay. So I mean, no need to worry up from being as a computer science fellow, but you try to understand that we have adopted, and you can find various ways in literature by which you can enhance the performance of the neuron architectures. Okay, layer reuse philosophy we have used maybe, and then yes, here yes. I mean, I have not shown many things, but we have used how many times you have to use, right? That is also one factor comes, and then we have improved the performance of the neuron architectures. So as of now, what we have learned? We have learned how to do the computing of neurons. I mean, the fundamental computing is the multiplication and addition and activation function. So these three blocks you can make using Verilog or VSDL digital design language. You can also design these neurons into analog approach also. Okay, so as a hardware person, we have to understand various data sets, for example MNIST data sets, right, or Cipher10 data. So Cipher10 data is the 10 classes of images, started from the bird, car, human, and so on and so forth. And then we have to also train various architecture of the neurons, which I am not showing here, like linear architecture, right? There are multiple neuron architectures out there. We have to train the model, we have to find and calculate the weight of the neurons, feedback somewhere else, okay. So ultimately what we are doing? We are trying to find out some trained weight of neurons, which is supposed to be stored somewhere else. Storing means we have to have some memory element, right, which I started with here, some memory element. So how to store such a huge data sets, that is the interest of the discussion, okay. So this is the recon architectures which we have developed in our lab, right, complete flow of the recon architecture, reconfigurable architectures of the neuron, where multiple layers are being used, so that the same layer can be used for various architectures. So this is how we have learned that how we can improve the neuron architecture, or how we can enhance the performance of the hardwares. Now a very interesting topic that was one of the outcome was the AI accelerators. So accelerator is nothing, is like once again the chip only, but since you are interacting at kind of data sets of images or video or whatever it is there, right. So your hardware should be competent enough, that is called the accelerators, which accelerate the performance of the chip. So all the components which are sitting, for example addition, multiplication of even all available blocks or sub blocks, that should be designed accordingly, so that can interface the images data sets, okay. So this is nothing special, okay, but your chip should be competent enough to deal with the specific networks, okay. So for example here, if you are taking the input size of 5 cross 5 kernel size, tried, and output you are getting 1 input. So these things once this is a vector multiplication. So these things you will learn and do the things, and then you will find out, and accordingly you can design, because here it will come multiplication, addition, everything is coming, right. So those things we have to perform in the background, and then you can calculate. But you try to understand that ultimately we need a sophisticated hardwares, okay. So now question is, which kind of hardware you should think of for edge computing? So for training the data sets, multiple variety of hardwares are available in the nature, in the market, right? So GPU is the one, right? Graphical processing unit is the one, FPGA and ASICs. So ASIC stands for application specific IC, which is small in size, very tiny chips. FPGA is little bit this much size, and GPUs are of course bigger in size. So if you try, and there are a large number of accelerators available by even Google, Intel, Xilinx, all these companies, they have their own accelerators, NVIDIA. Now the issue is that for edge AI computing, do we need such a big servers? Because they will consume power, right? So what kind of hardwares or what kind of accelerator we should, right? So that edge computing can be done with a small form factor, low power consumption, and without losing the data and maintaining the latency, okay? That we have learned in the few slides before. So GPU can also be act as an accelerator, right? But the advantages are with the GPUs are like, which of course the increase the speed of the computation. So if you have a huge data sets, for example image, so usually very easily you can compute on the GPUs, okay? And this is because of the efficient parallel processing, multiple cores are sitting, okay? And then the high bandwidth computation feasibility and ideal for existing ML algorithms. But limitations are of this kind of accelerator if you are using GPUs are high power consumption, because the big servers are there, right? And of course extreme heat generation is there. So maintaining a servers in the data centers is a very expensive, with the cooling effect basically, right? So the keeping servers is much easier rather than maintaining those servers into the cooling environment. So that is what now these liquid coolants are coming, where the entire GPUs are going to be put inside those liquids so that it can dissipate the heat of those complete servers. So you can see in the market. So GPU has also a couple of advantages and disadvantages, but bigger in size, more consume the power. So is it suitable for the edge? Not at all. How about ASIC? ASIC is a tiny chip, very small chip, okay? So ASIC is of course the optimal speed of transferring the data is optimum, not a big deal. Lower power consumption, which is the need of ours of edge computing, right? More application at embedded devices. So this may be suitable, but couple of limitations are there. So limitations are no flexibility, means once you design the chip, even it's very tiny, right, you cannot reuse, right? So that is the one issue with the no flexibility in nature. Long time to market means designing a chip, right, it requires huge, like 1 year, 6 months or even 2 years time, a big team also. Focus on various components, for example ADC, many blocks are sitting right here. So time to market is also very long in this, and of course the cost of implementation is very high. So because of these limitations, people are less preferred to ASICs, right? But FPGA is another class. So what is FPGA? FPGA is a field programmable gate array. So the plus point with the FPGA is flexibility of computation. You can do multiple times. You can write the code of the desired AI accelerators multiple times. If you are not satisfying your goal, you can reprogram, and that is called the flexibility of the system. It means it's a readily available chip which are placed on the board, okay, which I have shown in one of the beginning slide, which is reprogrammable. So flexibility is the one important. Reconfigurable is there, logic computation, high performance per watt is very good, right? But of course, low throughput. So this is the only reason that the complex programming required, of course, we need to know, right? So reliability and the efficiency and the flexibility, right? So ASIC is of course very efficient as compared to even FPGA. So FPGA is, for example, you try to understand if this is the server size, FPGA is like this much and tiny chip is like this much. This is a very form factor varies like this, okay. So because of this, but of course the FPGA is also not so small, but nowadays the Xilinx, now Xilinx is being taken care by AMD. So AMD Xilinx, they have come up with a very small form factor of a kind of stick, memory stick, or you can say the kind of pen drive kind of stuff, where you can deal with huge data sets. That much sophisticated FPGA they have come up into the market. Even Intel also they have come up with, right? So that is what people are trying to evolve. So the FPGA and GPUs and ASIC things are being shown over here: adaptability, availability in prices, user friendly, and power efficiency, right? So this is how ASIC is, right? Of course, availability and cheaper, of course. The price of the ASIC is very cheap, very cheap. Right? GPUs, CPUs, of course, low, and FPGA is a medium one. So that is what most of the people prefer, the FPGA as a potential candidate of training the algorithms in the hardware, and hence the design and development of those FPGAs are also very important. So can we think of rather the processor and many things on in-memory computing and so on and so forth, right? And once you are happy with your target, which you are sensing and everything, you can convert that FPGA board, that is tiny chip, into the ASIC using some softwares. So that is what majority of the people works on the hardware for FPGA, and if they are happy and okay, they can convert into tiny chips very easily, right? So as of now, I have explained what are the available hardware to deal with these neurons or neuron architectures, which is primarily used in AI or machine learning things, right? Now coming to the edge computing, or you can say the in-memory computing, right? Processor is there, and then of course memory blocks are there. So in early days, one human architecture, right? Both the entities are going to be at different blocks. So if you are keeping both the blocks and doing computation and storing together in memory, called in-memory computation, right? So so the data movement was one of the bottleneck in conventional computing architectures. This is called the von Neumann architecture, which was evolved many years before in computer architecture, right? So, and these operations, of course, you can do, not a big deal, so no need to explain, but you try to understand what are the latest memory technologies. I am directly jumping now. So SRAM is the most preferred destination, or the static random access memory. Then DRAM, flash, RRAM, PCRAM, SSCRAM, and many RAMs, many memory technologies has been evolved last 30-40 years. But still, SRAM is the most preferred choice even for in-memory computing. Okay. So now here also, if you see, the fundamental blocks is this MOSFET. This is called the MOSFET, which I was explaining here, right? MOSFET. So this is a MOSFET. Even this is an inverter. Inverter will also have some circuits. So inverter means if you are passing 1 here, you will get 0, or 0 then 1. So this is a cross-coupled inverter, and these two are access transistors, and these are the word line and bit lines. So one cell can be stored in this SRAM, right? So there are lots of advantages in technology and so on and so forth of these available memory technologies, okay? But even RRAM is also going to be one of the potential candidate in the coming days for AI application, right? Resistive RAM basically, right? So they don't have I mean this multiple mass transistors, only 1-2 plates are there, and in 2 plates you can that can be acted as a switch, right? So that is what the RRAM is also going to be a very potential candidate nowadays. Last couple of 1 year or so, a huge research is going on that how RRAM can be used to store or retrieve or compute even, right, in for AI applications. So in many places research is going on very heavily. In fact, many industries, they have already come up with couple of hardwares. That. So coming to the in-memory computing, just now I talked about that ultimately when you are dealing any kind of neuron or something, we have to store, we have to process, right? So to process and store the information, we need the memory, right? And we need to compute into the memory. Means storing there and processing also. Processing means some operation you are performing, for example addition. So to add the operation, we have 2 bits, right? Or multiply 2 bits, you need 2 bits, right? And store there as well. So this is, for example, bit line 1 line, so bit line 1, bit line 2, bit line so on so forth, bit 128 for example. Here word line 1, word line 2 and so on so forth, word line 128. Just now I was talking about here. Here this is the bit lines, bit line bar, and this is the word line. Okay, so one memory, this is the SRAM cell of which can store only one bit. So likewise, there will be multiple cells in an array. So the same has been shown over in the next slide. Said, for example, this is the bit line 1, word line 1. Here you can store one bit, and to store one bit, we have to have a combination of 6 transistor SRAM cell, which is shown over here. So likewise, all the points, right, we have to have 6 transistor SRAM cell here, 6 transistor SRAM cell here, and so on and so forth. So this is called the array. And then of course we have some peripherals, because bit line 1 and bit line 1 bar would be there, which is supposed to be sensed by sense amplifier, which will be placed here. And then how to go and hit this cell, there we have to have driver lines, row driver, column driver. So all together we call as peripheral circuits, which is not shown over here, but ultimately you have the sense amplifier, pre-charge circuits, decoder circuits, and so on. Multiple blocks would be there, and all together what I am saying, that is the peripherals. Okay, which will enables to store the information or retrieve the information from the cell or into the cell. Okay, this is called the array. This is called the array. The column would be there, sense amplifier, right drivers, right, various circuit block, row decoder. This is called the M cross N SRAM array. There are M rows and columns, and on each cells, right, which is shown over here, 1 dot, 1 dot, and so you have the like this. This is just simply has been shown 128 bits row and 128 columns. So you try to understand that with the concept of SRAM, how operation will be performed, operation of performing the addition, subtraction, multiplication, division, what we traditionally do in processor, right? In processing, what we used to do, 8085 processor, or recall, or 1880 processor, we have to pass some commands like addition process, right? So similarly, how to add, perform the addition operation here. Okay, so all those things will be here. For example, this is the 6 transistor SRAM cell. Okay, now this is the foundry 8 transistor. Means foundry means, as of now, last 50-60 years in the history of chip design, right, SRAM is, this is the one which is the preferred choice by all foundries, by either by Intel or any industries, right, in memory, especially SRAM. There are various custom 8, then 8 transistor, 1 capacitor. So there are even 10 transistor, and so on and so forth. So over the period of years, various configuration of memory cells has been evolved of these categories, for example, right. So you can think of to use this memory cell, and you can perform some operation. So what I was trying to explain, that over a period of last 40 years, there are various memory cells which has been evolved, even in SRAM category. There are various categories, right. So SRAM 6 transistor is standard one, but what happens with SRAM, you cannot perform many operation in case of in-memory computing. Okay, so people have thought of, even our group also evolved various architecture of the SRAM cell, by which we have performed various operation in the memory itself. So processing part and computing part, both we have done together, and not only we, but many other researchers. Okay, so these are the various memory cells, especially 6 transistor SRAM and its successors, and depending upon the advantages and disadvantages of each one, people preferred. Sometime 8 transistor, sometime the other one, sometime 10 transistor, and so on and so forth. Okay. Okay, so this is how we can compute in digital side and analog side, and so on and so forth. But here is the point of interest, that how SRAM can be used in computing mode. So if you see here, so this is the XNOR mode based read word line driver column, and if you see here, right, every rows and column you will have a cell, which just now I have shown, right. And then of course we have the decoder, and then with the sense amplifier you can take the output, right. So these are the techniques and the methods, okay, which applies to do the computing as well as the storing in SRAM, right? And here also you can see in one of the other work where convolutional SRAM, right, where they have used 10 transistor SRAM cell here for 1 bit, okay, and IMC based architecture for the CNN accelerator. As a software guys, you must have learned what is CNN, deep neural network. Low power and high throughput. Here there was some problem of the 614 giga operation per second. Row wise and charge sharing of the SRAM bit cell was placed, all row wise, okay. For example, row number 1, row number 2, weight number 1, weight number 2, and so on and so forth. And then they used to place ADC, and then from here you can take the conventional output, and here you can take this convolutional input, and the convolutional output you can get. So people have come up various ways to use the memory architecture in CNN accelerators, or you can say CNN computing memories, okay. Like this is the another accelerator, right, where in memory computing based hardware accelerators are being used. So various layers are there, okay, and these are the memory interfaces, like I said, sense amplifier and so on and so forth. So multiple XNOR SRAMs are being used by multiple times. I just said that reused feature. So layer will be used multiple times. So if you do this, then you can improve its performance, okay. So many people have come up with various ideas, layer by layer basis computation comes, okay, and double buffering schemes and time multiplex and reused over timing also. So this is complex architecture, but if you try to understand that how people have used this philosophy to do computing, right, for example, these are the neurons, right, which we have to follow, the train weight, activation function, multiple layers, and each layer are supposed to be stored in some transistor, SRAM cell, right. This is the one, like then you have to do filtering process, pooling process, all those processes you have to do in the hardware itself. So as a software guys, you may understand how to reach out to the complex output of the CNN networks. So we have to do the filtration process and so on and so forth, but ultimately as a hardware person, we have to evolve all those things into the hardware. So like here, right, all the neurons are here, 32-bit for example, driver lines are here, word lines are there, and each cells are sitting, okay. So how, for example, over here, so this is the 10 transistor SRAM cell where this complete MAC unit we have performed, multiplication and addition. As I said that in this AI part, right, machine learning part, we have to multiply the neurons and add it, which we are doing here, okay. And then if you have a 1 MAC here, 1 MAC and so on, so multiple MAC units are there, right, and in 1 MAC, how you are designing the efficient MAC, that matters, and hence the overall performance of the circuit will matter. For example, over here, seen over here, that the 3 input of 28 cross 28 image, okay, and then multiple times if you are doing all those CNN networks, then you will find. But every stages has to be passed on and store over here and do all those computational things, operations thing over here, right. So this is the one thing which you can, is timing analysis and so on and so forth, which we have to do. It's not like that you can just pass on and you can get the output. We have to follow various timing diagrams and timing requirement so that you can get exactly output what we desire, okay. So many things we have done, and we have used the in-MAC block, which was near memory computing, right, and various row drivers are there, column drivers are there. So initially what we did, like other researcher, we have also investigated using 6 transistor SRAM cell, okay, and later we realized that no, 6 transistor is not sufficient enough. You cannot perform a large number of operation like this, right. These are the operation, addition, subtraction and so on, so incremental, decremental we have performed. So what we have learned that couple of operation we are able to perform all basics but not advanced operation. So we thought of, can we use 10 transistor? So first what we did, we tried to investigate the analysis and performance estimation of the 10 transistor SRAM cell, which meets in memory computing. So we started doing all those analyses, and many things we have done at various blocks and at the hardware level, and we have designed this 10 transistor SRAM cell with Taiwan Semiconductor Manufacturing Unit node 65 nanometer, and we realized that even advanced operation, CAM operation and binary neural network operation can be also performed using 10 transistor SRAM cell very efficiently. So we have done all those stuff, right, and multiple MAC implementation for the neurons, right, the dot product is there and the many products are coming, right. So how to perform all those products and so on and so forth, so that ultimately your image, ultimately what you want to process through the various pooling and filtering process and so on and so forth, you can get its output. So what should be the relevant process of using SRAM architecture into the computing process that we have investigated, okay. And we have found that the CNN network with the MST datasets and ANN network with MST dataset with the accuracy of 98 and the corresponding binary network accuracy was 96, 97 point. So all those processes we have done into the hardware. This is probably the last slide. So overall framework of the SRAM based IMC, okay. So circuit level what we can do, bit cell architecture. So those who are from the hardware background or the electronics background, they can understand the bit cell architecture. What kind of bit cell you have to choose, okay, like 6 transistor SRAM cell, or 10 transistor, or what exactly, ReRAM, what exactly. So that we have to consider. Then the function level, what kind of functions you are performing, right. I mean the digital SRAM based KIM or mixed signal SRAM king, because there are purely digital side, then analog and mixed side, single bit, multi bits, CAM, Boolean logics. What are the functions you are performing, NAND, OR, NOR, binary CM, and many things are there. So these are at the next level called the function level operation of this in-memory computing. And then if you are performing everything perfectly fine, you can go with the application level. What kind of network you are training, right, CNN or the AES algorithms, what you are doing, right, everything you can perform. So this is the complete framework which will be used in the hardware accelerator design of this kind, okay. Of course these are the challenges and the possible solutions, right. If challenges are there, of course solutions are also there, right. So we have to have various optimized materials and the device structure, as I said in the very beginning, like MOSFET was the one, then the FinFET was one, there are multiple architectures, right, which can be potential application, right. Endurance and retention in the flash memory technology, these are very important, right. Multiple states, speed and power. So stability of the devices is the another challenge, right, which one has to think, because we are dealing huge data sets. So your hardware should be reliable, secure, safe, many things, right, and that should have a larger data sets which can be compiled. So these are the level where we can think of large scale integrations, new materials like silicon, maybe we can think of some other materials, right, and the crossbar array fabrication, the silicon technology, right, and then the system level application where algorithms for the physical application and peripheral circuits, they can also done by the system level, no need to design even circuits, right. So these are the few challenges and the possible solution, okay. So if you think about these stuff, right, the memories, right, which we have talked about just now, it's a complex actually understanding, but ultimately we have to design the energy efficiency, right, of the MAC operation. So your MAC should be designed in such a way that they should consume less power and very efficient, very high speed and so on and so forth, because in the entire neural network or the image kind of stuff, we have to have the dot product, I mean the multiplication, addition, and the pooling, filtering process will come anyhow, right. So how do you do all those things, right, in memory today I have covered. So this is the group where we belongs to. So she is Neha, right, the leftmost. Then Gopal, my PhD scholar, she was MS, she has also contributed very good. Sonu, PhD scholar, last 1 year he is contributing. Narendra is the PhD scholar, last 3 years he is contributing. And of course me, backside. Yeah, Vashundara, she is also PhD scholar, last 1 year she is contributing this area. Sumiran is MS research, last 2 years he is contributing. And Varun, MTech student, last 2 years they are contributing. So we have, this is this AI accelerator group. And apart from this group, we have various other groups where we are working on different dimensions of the research. So thanks to these people that they have contributed last 6 years or so in this important area of the research. So from my side done, this is my web page and this is the email address, and if you have any interaction, anything, so please let me know. We will be happy to help you anytime, and we will be happy to even take from you people if you are working in this dimension. So from my side done, and we can interact if any concern or any suggestion or even any other things. Yes, please. Okay, resistive RAM, great.
Yes, sir. I'm working on arithmetic circuit implementation actually.
Okay.
So we are saying it takes, if we take von Neumann architecture, it is taking only 0.1 picojoule for 32-bit addition.
Yes.
Whereas accessing 32-bit data from DRAM is 640 picojoule. May I know the reason for that? Is it because of the capacitive charging and
Capacitor
discharging?
charge, yes. And in your architecture, only capacitor is there.
Yes, sir.
RAM, only one capacitor. That is the top plate and bottom plate.
Yes.
Right? Resistive RAM.
Yes, sir.
So that is what your device is much faster than the DRAM.
Yes, sir. But if we take one general transistor based circuit, it is easy to understand because we say energy is always consumed because of capacitive charging and discharging. How to understand the same at system level?
But fabrication of the MOSFET is also very tedious and complex process. But
Yes.
fabricating two plates is very easy. Like, so that is what, even when MOSFET was not there, only this was there. Only this what we call is these things were not there. I'm just forget, they were not there.
Yes.
So only silicon dioxide layer was there, and then metal layer was there, and then silicon layer was there.
Yes.
So even early days, this concept was given. You got the point?
Yes.
And the same concept is being used by RAM people. So in early days, what you used to have, this is the silicon dioxide, okay, and this is the metal line, and this is the silicon line. So this is still the same, right? This and this RAM, two plates concept. But fabricating this part was very difficult. It took 60 years by the researcher, by the even foundries.
Yes.
So now probably what is my understanding, that the same philosophy which was like parallel plate structure
Yes.
is came, that is the RAM. So even we are doing research on SRAM, and recently last 2 years one of my master's students started with some German partners the same RAM based circuits and systems. So what we are doing there also, we have designed the in-memory computing and the cadence environment, and you can download RAM based technology file from IHP or even IMEC Belgium.
Okay.
You can easily download, where you can just connect and make any any operation over there.
Currently, I'm using a Stanford PKU model, sir,
Achha,
for my
PK.
simulations.
That also fine.
Sir, when we say 640 picojoule, where exactly it is going? People are asking me, you say 640 picojoule is consumed when we access 32-bit data from DRAM. Where exactly it is going? Like that energy, where it is exactly consumed during the transfer from memory to the processor?
I can't comment because I don't work on those area, but we'll discuss sometime because we are dealing only the SRAM side.
Okay.
But DRAM side, yeah, I mean DRAM is also one of the potential candidate because it with the only one transistor, one capacitor, you can store such a large number of data, right?
Yes, sir.
So like high bandwidth memory, HBM is there already there.
Yes.
But what I feel that what you are touching the area RAM is very good. Yeah, because the RAM is only one capacitor, right? Even no transistor is needed. So you can accommodate large number of data sets, right?
Yes.
And so since we have not performed much, the last 2 years I have given one task to one of my master students and he did a good job. But the one point which you are addressing, we have not focused upon. So we'll discuss sometime and we'll try to understand where is this power consumption is going on.
Sir, one more thing I would like to ask. When we use different models for the memory store devices, the operating frequency is varying. For example, if you take some SPICE model in LT SPICE or something, the operating frequency is different.
Okay.
For the Stanford PKU, the operating frequency is different.
And my suggestion is even it's come from the standard, you use the now this IMEC Belgium people and this IHP Frankfurt order.
Yes.
they have come up with standard industry standard RM models,
Okay, sir.
and you better use Cadence rather than the LT Spice.
Oh, yes, sir. Sir, this iMac one you're suggesting, is that open source? Is
Yes, you can easily download even from any foundries. Just we need to sign the NDA with them.
Okay, sir.
Okay, and maybe your professor, even you can sign that you are going to use that technology for your research and development purposes only. Okay, so they will give you access to download those technology file, and you can use in the Cadence environment like normal PDK we are using, right?
Yes.
So we have the process design kits of, for example, MOSFET 130 nanometer or any other models. So like those models, they have already developed actually.
Okay, sir.
So unnecessary as a circuit designer, we should not develop our own model.
Oh, yes, sir.
If possible in your research.
That is
We
another
can use
research.
that model because that is also well tested model, fabricated, measured data and everything. They have the technology file. And very easily you can, in fact, our general partner are very happy to fabricate those chip in the IHP only.
Okay, sir.
So even if you go with that model, you will have the tested workable results with you.
Yes, sir.
Right? That is my suggestion. Rest we can discuss because we are entering into the technical discussion and maybe. All right.
Oh, yes, sir.
Okay, good. So you are in PhD here?
Yes, sir. I'm a PhD scholar.
Okay, good. Yeah.
Thank you so much.
All right. Thank you.
Okay, thank you, Professor Vishwakarma, for a wonderful talk. I hope that students got an idea about not only algorithms when we talk about machine learning and deep learning, but we also have to look at, ultimately we have to implement it in the hardware and use the hardware. So it was a very informative talk. Thank you very much.
Thank you.
Now I would request Dr. Ramakrishna Gorti to give a memento to